This is the gripping conclusion to our video series on the ratio test and root test. In the last video, we showed the improved ratio test. Now let's give the root test the same treatment, and then we will finally reveal which test is better. The high school calculus version of the root test says to take the limit of the nth root of the absolute value of the nth term. If the limit is less than 1, you have convergence, and if it's greater than 1, the series diverges. The new version says that the sequence of nth roots doesn't even need to have a limit. Just take the lim sup of the nth roots of the absolute values. If the lim sup is less than 1, you have convergence of the series, and if the lim sup is greater than 1, you have divergence. Notice we don't even need to use the lim inf for this test. Let's do the convergence case first. This is quick and the method should look familiar. We will let big L be the lim sup of the nth root of the absolute value of a sub n, and we are assuming that L is less than 1. Just like in previous videos, we let epsilon be 1 minus L over 2, so that L plus epsilon is strictly less than 1. One of the properties of lim sup says that past some term big N, all the terms of the sequence are less than L plus epsilon. So for all little n greater than or equal to big N, the nth root of the absolute value of a sub n is less than L plus epsilon, which by design is less than 1. Raise both sides to the nth power, and we see that the absolute value of a sub n is bound above by L plus epsilon to the nth power, and that is a convergent geometric series. That gives us convergence, and we are done. Now for the divergence case, we are given that the lim sup of our nth roots is greater than 1. So that means there is a subsequence of terms that converge to L, which is greater than 1. As before, pick epsilon to be half the distance from 1 to epsilon, and there must be infinitely many terms that are within epsilon of L. So there are infinitely many a sub n's where the nth root of the absolute value of a sub n is between L minus epsilon and L plus epsilon. And of course, remember that we set things up so that L minus epsilon is greater than 1. Raise everything here to the nth power, and we see that there are infinitely many a sub n whose absolute value is greater than 1. Well, that means our a sub n's pretty clearly flunked the zero test. The terms can't have a limit of 0 if we can always find another term with magnitude greater than 1. Since it fails the zero test, we have a divergent series. One way I like to think about the root test is that it is looking at the long-term trend of the values of a sub n. Consider the graph of the curve r to the n, where n is on the horizontal axis, and r is a number strictly between 0 and 1. The convergence case of the root test says that we need to make sure that the a sub n's eventually stay below that curve, and since that curve represents the terms of a geometric series, this means the original series will converge. Since we're taking the lim sup instead of the plain old limit, the a sub n terms don't need to asymptotically approach the curve. Instead, some of the a sub n's could be much lower. But here's something really interesting. Let's say the a sub n's are closely following the curve, that is to say they are dropping off like r to the n, which is another way of saying that their nth roots are hovering around r. But then suddenly we have a really small a sub n, but then the next term goes back to hugging the curve. No big deal, right? Our terms are still being dominated by r to the n, so we're good. Heck, let's make every other term in our series really small. Making some terms smaller can't be bad for convergence, right? Well, that's correct, but it's interesting that this could completely throw the ratio test for a loop. The ratio of successive terms in this case could be huge. And if this sort of thing happens infinitely often, then even the lim sup of the ratio of successive terms will be really large. This means the ratio test would fail here, even though the root test would show that the series converges. Another way to put this is that the ratio test is very sensitive to small fluctuations in the terms. It's effectively asking, what have you done for me lately? The root test is more circumspect and has no problems with these small blips. Intuitively, this is why the root test is actually stronger than the ratio test. Imagine we collect all the series that pass the ratio test for convergence. They would be strictly contained in a set whose members are all the series that pass the root test. To give one quick example of a sequence that falls in this part of the Venn diagram, start with a geometric series with r equal to 1/2. The nth root of a sub n is 1/2, and the ratio of successive terms is 1/2, so this clearly passes both tests. But now divide every other term by 10. We've made the term smaller, so it clearly still converges, and the lim sup of the nth root of a sub n can't possibly be any bigger, since we didn't make a single term any bigger, so the new series must pass the root test. But every other ratio is 5, so the lim sup of the ratios is 5, the lim inf is 1/20th, and the ratio test gives no information. Remember, we need the lim sup below 1 or the lim inf above 1 to use the ratio test. This should give you a good understanding of what makes the root test stronger, but if you insist on seeing a real proof, then here it is. We're going to start with a series that passes the ratio test for convergence and show that it also passes the root test. So we'll let big L be the lim sup of the sequence of ratios, which will be less than 1, and as usual, we will let epsilon be half the distance from L to 1, so that L plus epsilon is also less than 1. Then starting from some big N, all the ratios are less than L plus epsilon, which is less than 1. So the absolute value of a sub big N plus 1 is at most L plus epsilon times the absolute value of a sub big N. The absolute value of a sub big N plus 2 is at most L plus epsilon squared times the absolute value of a sub big N. And in general, a sub big N plus k is at most L plus epsilon to the k power times the absolute value of a sub big N. Now k is the number of terms past big N that we've gone, so just to make the algebra clearer, I'm going to write little n for big N plus k. So that last line becomes a sub little n is less than or equal to the absolute value of a sub big N times the quantity L plus epsilon to the quantity little n minus big N. Rewriting a little more, the right-hand side can be written as L plus epsilon to the minus n times the absolute value of a sub big N times L plus epsilon to the little n. To make this look like the root test, we can take the nth root of both sides, and then we get that the nth root of the absolute value of a sub n is at most some constant to the 1 over n times L plus epsilon, where I've written c in place of the constant L plus epsilon to the minus n times the absolute value of a sub big N. The important thing to note here is that c is positive and independent of little n. And if we take the limit of the nth root of a positive number, we get 1. If you're not familiar with this fact, it's a good exercise to prove it, and we have a YouTube short proving the harder case of taking the limit of the nth root of n. Now, we have to be a little careful here. It's tempting to take the limit of both sides of this inequality. The right-hand side has a limit of just L plus epsilon, but the left side might not have a limit. That's the whole reason we have the new and improved root test to deal with these cases. But we can instead take the lim sup of both sides. It's not hard to show that if the terms of the first sequence are less than or equal to the corresponding terms of the second sequence, then their lim sups follow the same relationship. So this gives us that the lim sup of the nth root of the absolute value of a sub n is less than or equal to L plus epsilon, and we know that's less than 1. So the root test works on this series, and we are done. We'll leave the divergence case as an exercise, but just to set it up, you're going to assume that the ratio test indicates your test diverges. In other words, the lim inf of the absolute value of a sub n plus 1 over a sub n is greater than 1. You need to show that it also passes the root test for divergence. In other words, the lim sup of the nth root of the absolute value of a sub n is greater than 1. You can use the fact that the lim sup of that sequence is at least as big as the lim inf. So we see that whenever the ratio test works, the root test also works, and there are cases where the reverse is not true. So that makes the root test better, right? Well, in some sense it does, but the real reason the ratio test is so valuable is that it's just easier to use sometimes. Take something simple like the sum of 1 over n factorial. You can apply the ratio test in your sleep, but try taking the nth root of n factorial. You can do it, but it's far easier to apply the ratio test. Now, factorials appear constantly in power series, so this is no minor issue. So in some strict logical sense, the root test is better, but for actual series that you're likely to see, it can go either way. And that concludes our series on the ratio and root tests. Or was it a sequence? Anyway, subscribe to find out about other videos we release, and let us know in the comments if there are other topics you want us to cover. As usual, hitting the like button helps us produce more videos like this one in the future. On behalf of Nick and myself, thanks for watching.